Okay, number 6. So U.S. Postal Service package. They only accept packages for standard shipment whose combined length and girth are at most 108 inches. Girth is defined to be the distance around the package, or put simply, the sum of twice the height and twice the width. If a package has a square end, i.e. height equals width, what are the dimensions that will maximize its volume? Okay, so if we define volume as length times width squared, which if it's a rectangular prism, we definitely can't. With a square end, we can. So we say that is one of our equations, and then the other restraint is that our girth can be no more than 100, or it has to be equal. To maximize the volume, we'll take the most. So that'll be length plus 4 width. Did they say that? The sum of twice the height and twice the width. Okay, sorry. I was hung up. I was like, wait, if the girth is 108, that would just be this part here. So like, what's the L? It says combined length and girth. So that's L plus 4W. All right, that's the whole thing. So now we can start to plug in some of this stuff here. If we want to solve this for L, we would say that L is equal to 108 minus 4 width, right? So then we can rewrite our volume equation as 108 minus 4 width times width squared. And then we can distribute that out to get 108 W squared minus 4 W cubed. Take a derivative. So that'd be, what's that, 216 W minus 12 W squared. Set this statement equal to 0. So that'll be 216 W equals 12 W squared. Do you follow that?
Yeah.
Okay. And then if we divide each side by W, we'd get 216 equals 12W. And then if we divide each side by 12, we'd get W equals 216 over 12, which I get 18. So then we need to do an analysis of sines. Can we do an analysis of sines? They do a second derivative. Which I guess is another way to do it. I wonder if we do if we do like a regular peanut butter and jelly analysis of V prime for 17 and let's say 19. I get 216 times 17 minus 12 times 17 squared. I get a positive number, which is good because we want a maximum here, so we want positive and then negative. And then if I redo the analysis at 19, I should get a negative number. And indeed I do. Negative 228 and 224 were those two numbers, in case you're wondering. Like I said, the numbers are kind of irrelevant. We just really want to see this pattern playing out because this implies...
There's the max.
Let's see, how should we write this? This implies V prime has a local max at W equals 18. So then the dimensions to maximize the volume, you just plug this back in. So I think it was volume equals L times the W, or no, I'm sorry, the one we'd want to plug into is the one with numbers, 108 equals L plus 4W, so 108 equals L plus 4 times 19 is 76. So L equals 108 minus 76, which is 36. Yeah, so pretty much all of the word problems that involve optimization of any kind are going to involve getting one equation. You're probably going to need to come up with 2 equations. Use one of them to solve for one of the variables, right? And typically these equations will involve two variables. So that's why you need two equations. So get that, solve one of the variables in terms of the other, plug that into the other equation, take a derivative, set it equal to 0, prove a max or min, and then you plug that number into the original constraint, one of them, it doesn't matter which one, although there's usually an easier one.
Okay.
And then you'll be able to solve for the dimensions or the time or whatever it is.